Welcome back, everybody, and welcome to this session on machine learning and quantum machine learning. So last week we discussed support vector machines, and there's a reason why we would like to move from classical support vector machines to quantum support vector machines. And one of the reasons for that is that there are many, many similarities. And the difference is obviously that we would need to prepare the states in a specific way. And then we are going to run a simulation in a kind of hybrid environment where we will calculate gradients classically. And we will also do the final linear algebra part classically. But we will evolve the states on a quantum computer. So these are often hybrid methods. So support vector machines have also been very popular. And the basic idea now in these kind of intermediate steps, which we need, is to look at classical kernels and then transit to quantum kernels. And then at the end, we're going to look at quantum support vector machines. So for the quantum part, there's actually a very good textbook by Claudio Conti, which in these sections, which you see here, and also chapter 2, elaborates many of the details. Also, I borrowed for many of the lectures a lot from Maria Schulz's article here, where she shows a kind of almost formal link between the classical kernels and quantum machine learning kernels. And one of the claims is that supervised quantum machine learning models are actually what we might call kernel models. So I will, however, repeat some of the things which we did last week about the classical support vector machines, just to remind you of some of the machinery which we went through last time. So the quantum machine learning, as we mentioned, integrates quantum computing with machine learning algorithms in order to exploit quantum advantages. And it explores also how quantum computing can enhance classical machine learning. And one of the motivations behind this is that you have a high dimensional Hilbert space for better feature representation. The hope then is that you are able to encode many more features than you have classically, and the quantum parallelism for faster computations, and then you have quantum entanglement for richer data encoding. So these are some of the benefits which you hope to use. Now, for quantum support vectors machines, it's not fully obvious whether we can exploit all these features, and I will come with some critical remarks, which you will also find in the slides here with links to the scientific literature. So when we have set up everything, we are going to illustrate how we can encode this using libraries like PennyLane, which is really tailored to quantum machine learning algorithms. Alternatively, there are also examples on how to use Qiskit. So the quantum thing, as we have discussed many, many times now, you can process multiple states simultaneously, correlated states for richer information, and then you have constructive and destructive interference to enhance solutions. These are some of the basic properties. There are obviously limitations. There is a lot of noise in quantum circuits. Decoherence and limited qubit coherence times are very important. Data encoding, efficient embedding of classical data into quantum states is highly non-trivial, and you will see examples of that today. And then it's also difficult to scale circuits to large data sets. So these are some of the many of the drawbacks here. So last week we discussed the basic mathematics of a classical supervised learning method, which is called support vector machines, where the basic idea is to find a margin which allows us to define a plane which separates different classes. And this margin is defined something which is called a support vector. So that's the distance in for a binary classification problem where we would just have a straight line in a plane. Then the support vector is defined as a distance from the line which divides the two classes to the nearest observation. And this is the information which we would keep track of. And at the end, what we end up with is a convex optimization problem where we define a Lagrangian with Lagrangian optimization parameters. And then we have the input data and the output which we want to reproduce. So the input data could be a number of patients. There could be specific features for a specific disease, and the output could be just a binary one, ill, not ill, or other types of classification types. We can also run this for regression type of problems, but support vector machines in their original derivation, they were really tailored to classification problems. And what we looked at last time was a typical binary classification problem where you have this true false situation. But as I said, you can have many more classes as well. So there is no problem in doing that. And one of the things which we introduced last time, which I wanted to repeat, is actually this kernel trick, which then relates the classical support vector machine with a quantum support vector machine. So it simply replaces the classical kernel, which you can often think of as a feature map, because the classical kernel is a way to represent the input data, which then encodes all the features which you have. So a typical feature could be if you're looking at a data set which does not have to do with any type of sickness, it could be a data set which reflects whether you will pay your credit card debt or not. So one feature could be the age of the credit card holder. Another feature could be the education of a credit card holder. Another one could be the sex, or type of occupation, etc. And then you would like to correlate all these features with whether this person will pay the credit card debt in time or not. So this is a typical example of a classification problem which has a binary outcome, paying your debt, not paying your debt. And then you can have many features which are then used in the training of a model. There's a famous data set which is I think it's called the Singapore, no, it's a credit card data set from either Taiwan or Singapore with something like 30,000 credit card holders and with something like a 20 number of features. So what you would do then is to encode this into quantum states, and this is called a quantum feature map, and which actually is a parameterized quantum circuit. And the inner product between two such states serves as a quantum kernel, and that measures the data similarity in a high-dimensional Hilbert space. And actually, many quantum models, even including quantum neural networks, which we will discuss next week, they behave like this kind of kernel methods. So we're going to spend some time on these kernel methods today to link both the classical ones with the quantum mechanical ones. And the quantum ones, they would typically analyze data in exponentially large Hilbert spaces. And this article by Maria Schult is an article I would typically recommend to take a look at. And she actually shows that supervised quantum models can be reformulated as support vector machines whose kernels compute the distance between data encoded quantum states. And these are the things which we are going to look at closer today. So in the classical case, these kernels help with the nonlinear data separations, and quantum computers can normally speed up the computation of complex kernel evaluations by efficiently simulating an inner product in an exponentially large Hilbert space. Keep in mind that the classical support vector machines, they do have their limitations because at the end, we end up with a linear algebra problem and a convex optimization problem, which is typically solved by linear algebra methods, which again means that the dimensionality of the problem can quickly limit the capabilities of classical support vector machines. So I'm going to skip some of these things. I wanted to talk a little bit more, remind you a little bit about the support vector machines, the classical ones, and what we did last week. So let's do quickly this repetition after this kind of general motivation. So the aim of the support vector algorithm is to find a hyperplane in a p-dimensional space. So we looked at just yesterday, we looked at a simple, not yesterday, but last week, we looked at a binary problem where But the binary problem is one where we have a typical output of the false true, etc. But you could have many features. So P is typically the number of features that distinctly classifies the data points. So in a p-dimensional space, a hyperplane is what we call an affine subspace of dimension p minus 1. And in 2 dimensions, as we looked at last week, this is simply a straight line, while in 3 dimensions, it's a 2-dimensional subspace, or as we would call it, just a plane. And last week, we defined the so-called margin between classes of a binary problem. And then we derived a margin M with a normalized vector, which is then used to define a vector which is normal to this hyperplane or straight line in the 2-dimensional case from a given reference. Then, with that, we found a condition here where we have the output, which could be a binary problem, true, false. And then we have these vectors, which we need to find. These x's are the input data, and then this b plays the role of a bias, which you may be familiar from neural network calculations. And this is supposed to be larger or equal to this point m. And this hyperplane can then split two faces or more faces or outputs. And then the whole idea is actually to set up a problem where we optimize, either maximize the margin or minimize the weights here. This W is normally called the weight. So what we had then was that we defined this W when we multiply away here. So we're actually seeking the largest value, which is defined by this equation. So we multiply away the norm of the vector W, and then we can require that this quantity here, which we have on the right-hand side, is equal to 1, so that we end up with this problem. And then we can either maximize M or we can minimize the norm of the vector. So we have thus defined our margin as the inverse of the norm of this W. And you want to minimize the norm in order to have a as large as possible margin. And this was basically the setting which we went through last time. This led us to a problem which we can then set up rather easily. And we would then have a Lagrangian where we have a Lagrangian multiplier because there will be conditions on the data. And the condition follows from this equation which we have here. We want these products to be large equal than 1. We know that in principle this is normally large equal than 0 if we have an output of the type y equal to plus or minus 1. And the output then is then multiplied by the model which we train. So we know that if y of I is equal to plus 1, and we train wrongly so that we produce minus 1, then clearly this is not large equal than 1. And if we train correctly, then this is large equal than 1. If we train wrongly again and y of I is minus 1, and this is plus 1, then we do not obey this condition again. So this is the condition which we have to obey for every y of I. And for every y of I, that introduces a Lagrangian multiplier, which we then multiply with this equation here. And then we want to minimize the norm, and we put a factor of 1/2 in front of it, because when we take the derivative with respect to W, either here, or both here and here, then the factor of 2, which we get from the derivative of the norm, is cancelled by the factor of 1/2 here. So the Lagrange multiplier, they're also subject to the condition that lambda y should be larger or equal than 0. Then in order to find these quantities, we typically just set up the derivatives, and we would use let's say, the Euler-Lagrange equations in this machinery, and we find the conditions on the parameters b. That gives us now that lambda y times y of I sums to 0. Similarly, we find the condition on the gradients from for W, the weights, which we want to find through the optimization. And that when we insert that back again, we have this equation here, which is then subject to the constraints that lambda y is large equal than 0, and that the sum over lambda I times y of I is equal to 0. So this is the kind of constraints which we get. And these are collected under the name of the Karush-Kuhn-Tucker condition. So we must satisfy this condition here. So if lambda y is larger than 0, then this quantity is equal 1, and we say that x of I is on the boundary. And if this one is larger than 1, we say that x of I is not on the boundary, and we simply set lambda y equal to 0. And then when lambda y is larger than 0, the vectors x of I are called support vectors. And they are the vectors which are closest to the line or hyperplane and define the margin M. So that this margin then defines the distance from this line or hyperplane to the closest point. And what we did then was to rewrite this equation in terms of a more compact vector matrix formalism. And this matrix, which you see here, is normally called the Gram matrix. And later we will see that we can redefine this in terms of a function which now maps the data into a new data set. And this mapping is something which is done with this kernel technique, which we will discuss subsequently now. So you can write this in a more compact way, where we now have also this condition here, where we summed over the y's and multiply with the lambdas, which is simply given by a vector times the vector lambda here. And the last step, when we solve the problem, that gives us the values for lambda I, and then we can find the coefficients of our hyperplane. We simply need to compute the weight vector W, and then we can in turn find the value of the intercept B. In this case is done for the two-dimensional case, which then results in this case here. And we can actually set it up by summing over all ns here, which is the number of support vectors. And that can then be used simply to make predictions later. So with the hyperplane coefficients, we can use our classifier to assign any observation by simply using this quantity here. And last week, we discussed also how to find the optimal values. One of the things which we also discussed was the introduction of what is called a slack parameter, because we may not have all cases being on the margin or above the margin, but we can actually allow for a kind of slack in the sense that you allow points to be on the wrong side of the margin. And then you would introduce the so-called slack variables. And you would modify the equations then, instead of having this equal to 1 when you're on the margin, we now allow for a specific slack where the condition is that this epsilon, now this psi of i's, are larger or equal than 0. And the total violation then is just given by the sum over all these violations. And this psi of I may be 0, it can be 1, etc., etc. And this psi of I in a constraint, the last equation, corresponds to the amount by which the prediction is on the wrong side of the margin. Hence, by bounding the sum, you also bound the total amount by which predictions fall on the wrong side of their margins. And misclassification occurs then when this psi of I is larger than 1. So typically what you will find then in most implementations, numerical implementations in most libraries, you will find a value C, which then by some value C, which bounds in turn the total number of misclassifications. And this is something you can plug in as an input variable to the calculations. So when you add the slack parameter, the optimization problem changes a little bit. So you have 1 minus this variable C, you have the bounding on it, and then we have a new Lagrangian parameter which we need to set up in the optimization. So in addition to taking the derivatives for finding the gradients and optimize, we took the gradients with respect to W, the weights, with respect to lambda, with respect to B, and now we need to take the gradients with respect to this gamma y and this xi of I. So that means that we end up with a new set of equations. This is actually not very difficult. And the optimization problem, which you end up setting, is actually a pretty straightforward one to solve numerically. So I'm not going to go through much in detail here, because what I would like now is to make a connection between quantum, the classical ones, and the quantum ones. But before we do that, I wanted to remind you of some of the things some of the codes which we run last time. And so let me bring up the Jupyter notebook and then take a quick look at some of the notebooks which we have here. So if we then scroll down a little bit, so this is essentially the material which we went through now. What we are going to look at is first a case where we can have, so this is the way we would typically use this kind of transformations. So the kernel transformation, which I mentioned briefly, is something which you can use to reshape the data. So if your original data is given by x1d, which looks like the figure which we have to the left, then it would be very difficult to find a line in this case where we have a binary problem with two features, x1 and x2, and we have two outputs, squares and triangles. So the features are given by x1 and x2. And then when we now plot everything here, we see that it's very difficult to figure out how we can separate the two outputs, whether it's squares or triangles. If we square them, however, then we'll see now that the squares can be separated by the triangles by just looking at this simple line here. So this is something we could have done with a linear regression problem, just to find the line which separates the two faces, or no, the two outputs. But the trick which we did here, so here we actually squared the results, and this is given by this new data set, x2d here, which is then the original one squared. And when you plot it, then you see that now it's intuitive to set up a straight line which separates. So the kernel trick, which is used in these methods, is actually to note that what you did here is nothing but a dot product of two original vectors. And instead of us computing the product in the Lagrangian here, we simply compute the dot product. And this leads to the so-called kernel trick. So here's another visualization of it. So you could have a data set which looks like this, and then you find a kernel which transforms your data, and then you have a decision surface here which separates the two classes you want to predict. And this makes the task of prediction much, much easier. So this kind of trick with the kernel trick is actually what makes the connection between a classical support vector machine and a quantum support vector machine. So the problem to solve then, instead of writing this, now this z doesn't need to be the original x. So keep in mind that the original x, that is the original data. So if you look at this figure which you have here, you have two features, two input variables, x1 and x2. So this could be you trying to find a model which predicts whether the grade you will get is correlated with x2, the number of hours you studied, and x1, the number of hours you slept. So you could now have a set of data where you simply measure whether this person gets a grade above or below the average. So this straight line here could be the line which separates a grade above the average and a grade below the average. And x2 and x1 are the features which then represent the number of hours you slept and the number of hours you studied for that specific course. And then you would perform a mapping from the original data, x1 and x2, the input variables. These y's are your outputs. So this function is then multiplied this case, then multiplied with the outputs we want to set up. So this is the matrix, and it also has a name in the literature. It's called a Gram matrix, GRAM. And that leads to a convex optimization problem where we have the specific constraints here. And the matrix elements are those which we have discussed previously. And you have different types of kernels. And the radial basis function one is the one which is often used when one makes the connection between a classical support vector machine and a quantum support vector machine. And if you go into chapter 2 of Claudio Conti's text, you will find in section 2.5 an example on where the radial basis function is being used. And there are obviously many other ones. So the thing is that the kernel trick involves implicitly mapping the input data into a higher dimensional feature space where a linear separation is possible. So sometimes you have no idea of what kind of possibilities you have and what kind of kernels you should use because your data contains many features. In that case, what people end up doing is simply to try different types of kernels. So this approach then obviously avoids the computational cost of handling high dimensional spaces explicitly. So instead of explicitly transforming each data point using a mapping function, the kernel function computes the inner product directly. And what you end up with then is actually computing a quantities which looks like this. And if you have a linear case, which is the one we looked at, then this would simply be given by, if these are vectors here, the xi would simply be xi transposed. So these are bold-face quantities because we have a vector which encodes the input features. And similarly for the xj's here. Here I wrote them in terms of v and w just to indicate that these are generic vectors. And the example here is actually an example where I have a binary classification problem, and I make 3 different data sets. So I'm setting up, I'm scaling the data, by the way. So there's a data set which is called the moons. So it makes distinctions between 2 classes. So in our case, these are squares and triangles again. But you could have circles if you want to. I just chose triangles and squares. And what I'm also doing is to make different transformations, as you can see. So I have a plain linear one. This is my first one. Then I have a Gaussian RBF here. And I also have an X3 here, which is also another Gaussian one, but where I choose different variables for the slack parameters, and also different variables for the value. If you go back to the equation for the Gaussian, you will see now that there is a parameter gamma here, which we can set up. And that is a parameter which we can play around with. So the what you would see then here when you run this code is that this is the original data. And in this particular case, it can actually be difficult to find a straight line here, which separates the 2 classes. Here now, you would like to, if you were to draw a boundary, this is the kind of boundary you would like to have. You could have some slack, as you can see. You have some of the triangles which are in the wrong side, and the same with some of the squares which are on the wrong side. And in this case now, we have a slack parameter 5. I have to remind myself of what D is. I think that's the yeah. I need to look back at what those parameters were. But then you can play around with different slack parameters. If you look here, you can make the slack smaller, or you can make it larger. And then you see now that when you make it larger and you have this gamma in front of the Gaussian, the radial Gaussian, the radial Gaussian basis function, then you can catch more or less of the data points. So these are typical ways you would play around with the classical support vector machine. Now, another data set which I wanted to introduce here is the iris data set. This actually classifies petals of flowers. And it's a famous data set which you will find in scikit-learn, which is a popular library. And you can see I'm using scikit-learn, so I'm importing the support vector machine. And this is the iris data set. And I do the standard scaling, min-max scaling of the data. I split the data into test and train, as is pretty common. So my test size is now 25% of the data. So this is not used in the training. So I use 75% of the data to train. And then I can now make a prediction, train a model where I've used a kernel, which is a radial basis function. So this is this Gaussian type of kernel. And I don't have a slack parameter in this specific case. And the accuracy score is the number of correctly predicted data in the test set. And you can see that that is actually used. So I train this on the train data, and then I make the prediction, obviously, on the test data, which you can see here. And if you look at the accuracy which just sums the number of correctly predicted events, so I have an accuracy of 1.0 here. So this is pretty good, actually. And this is the time it uses, which is actually not much. It's also a small data set. So when it comes to the quantum support vector machine, what then happens is that the idea here is that if you think of the classical one, we have a set of points that are in either one group or another, and we want to find a line that separates these groups. And this line can be linear, but it can also be much more complex, which is then something which we achieve by using kernels. So in a quantum support vector machine, there is an encoding part, there's a processing part, and there's a measurement part. So the encoding part is now the mapping to quantum states, which we will look at in more detail after the break. And the input data is first encoded into quantum states. And this process is something which we call a quantum feature map, where classical information is represented in the quantum Hilbert space. So it means that the data which we have, the input data, are now going to be transformed and encoded into quantum states. Then the basic step is a quantum kernel. This mapping enables the computation of a quantum kernel where the similarity in a product between quantum states is evaluated. And this quantum kernel can capture complex relationships in data that might be challenging for classical kernels. Then we have a quantum circuit processing. We have quantum gates and circuits, and once data is encoded, a series of quantum gates is applied. And these gates manipulate the quantum states to perform the equivalent of the support vector machine algorithm optimization and decision-making steps. And then there is a measurement, and the outcome after the quantum operation is a measurement is performed on the output state. And the result of this measurement provides the classification outcome. And that's pretty analogous to deciding on which side of the hyperplane a data point lies. Now, with all these words, it's actually time now to switch over to the whiteboard and look at the definitions of these kernels, which enter the optimization, the classical optimization part. And then we are going to use that as a springboard into a quantum kernel. So the first step we are going to do is to link a classical kernel with a quantum kernel. And when we have that, then we can start setting up the basic quantum circuit processing and perform the final measurement. And you will find the example codes below here, both in Qiskit and with PennyLane, which, as I mentioned earlier, is a very popular library. So let's switch over to the whiteboard and go through some of the technicalities which we need to look at. So what we did now was to mention or set up these kernels in the optimization part. So we had a Lagrangian, which without the so-called slack parameter was then given by an identity matrix of dimensionality n times n, where n is the number of data points, minus 1/2 multiplied with the Lagrangians, which is now given by the Lagrangian multipliers, which is just given by this vector transposed. And then we had this matrix P, and then we had lambda here. And this matrix P is a matrix which is now defined in terms of the input variables and the kernel, which then maps into a more complex space, and in the output variables. So what we had then was a y1, y1, and then we have the kernel here, and we had an x1, and I'm putting vector signs because these are not necessarily scalars. And then we had a y1, y2, so this become the matrix elements of this gram matrix. And then a x1, x2, etc., up to y1, yn, the number of entries which we have, and k of x1 of xn. And I should have space for and then we have a y2, y1 of k of x2, x1, etc. And this goes all the way down to y of n, y of 1, k of xn of x1. And finally, yn of k of xn of xn. Now, if you look at these components, what we also mentioned was that these are given by the inner product of two vectors, but let's just wait a little bit before we do that. So we also wrote this as a lambda, as an L, a Lagrangian, from I equal 1 up to n of lambda of I minus 1/2. And then we had a double sum ij, and then we had the lambda I, lambda j, and yi of yj multiplied with this quantity here. So in case it's linear, which was the example we looked at last week, then this k of xi, xj was simply given by the vector xi transpose times the vector xj. So I'm putting vector signs here in order to distinguish properly between a boldface quantity, which I normally use in my lecture notes, and a scalar quantity. So we assume that the kernel is symmetric. This is a common assumption to make. And then what I'm going to do now is simply to redefine the parameters yi times lambda of I. I'm simply going to call them for h of I. So one of the basic assumptions which we make is that this quantity, if this is the case, and it's normally the case for most types of kernels which we end up looking at, k of x of I of xj, so this is actually the kernel here, is larger or equal than 0. For each, you can actually prove this, et of n, and these h of i's are assumed now to be real numbers. Now, if that is the case, then there is a mapping. And this is just one of these theorems which we are going to state. We are not going to prove that. This is actually a rich literature on these topics. And there's a mapping which we are going to call phi of x, such that this k, the kernel, can be written as and then we have k of x of I, xj, is given by this function phi of x of I transpose times phi x of j. And again, if we think of the linear case, which we discussed last week, this is just given by the vector x of I transpose times x of j. If we have a Gaussian or radial basis function, this is obviously given by a Gaussian, and then we can have many, many other types of kernels. This becomes then a set of parameters which we then can include in the optimization part. So when we are running the optimization, what we often end up with then is this type of optimization problem. Now, the thing which is interesting then is if you also look at this specific equation which we have, we can rewrite it in terms of the following. And this becomes equal to the sum of I equal 1 up to n. And then I have this h of I, which contains the Lagrangian multiplier, and it contains the output y. So the Lagrangian multiplier is the quantity we want to find. And you will see later that when we are looking at these equations, this is something which translates into a simple linear algebra problem. Then we would have the function phi of x of I. And then this is again multiplied with the j equal 1 up to n. And then h of j of phi of x of j. And this quantity here is assumed to be larger equal than 0. So it's a semi-positive definite quantity. Now, the thing which we want to do now is actually to have an intermediate step, because if you look at this function which we put up here, we could now define a function which maps our data, can define a function which I'm just going to call f of x of j, which then could be given by I equal 1 up to n. And then we have the lambda of I, y of I, which we relabeled as this h of I here, multiplied with k of x of I of x of j. So then we can, if you think of what you have here, you could think of you making a mapping of an original data point through this kernel. So the function which you see here is the one which now we are going to elaborate a little bit on in order to find a connection with the quantum mechanics. So this function is actually interesting if we link it with elementary quantum mechanics. So we know that in quantum mechanics, in QM, quantum mechanics, a state is a linear superposition of a special function, which is, for instance, the functions which are the eigenfunctions of a given operator. It could be the energy operator. A state is a superposition of special functions. And these special functions are often the eigenfunction of a specific operator. And they are normally orthogonal and normalized. And we normally call them orthonormal functions. And you're pretty familiar with that. So if we could take just a given Hamiltonian H, it could be the harmonic oscillator. We don't need to specify that. Then we know that when this acts on a state, we have an eigenstate and an eigenvector. So an eigenstate and an eigenvalue. And then we could now expand any state in this basis here. And in principle, this basis is actually infinite. So we end up with a C of n, phi of n of x. So, and what we want to do now is to try to link this with the expression which we set up here for this function f. So the question is, how do we link this equation, which now you see also links the kernel with this function, which performs a mapping of xj, and how can we link that one with an expression like this one? So let's give this expression, which we have here, a specific number. So we are going to call this for expression asterisk tilde. No, this is just the asterisk. And then we are going to try to find the link with that expression which we have here. Now, the problem with this expression is obviously that we have an infinity of states. Normally, when we perform quantum mechanical calculations, we always do a truncation. In the equation which we have here, we have a finite set of observations. So let's now take a break first, and then after the break, we are going to look at the link between this equation, which you see here, and the classical kernel definition of the function f of x of j. So before the break, we looked at the possible link between the kernel function expressed by this function f and the kernel itself, this function k, and quantum mechanics, because this is what is going to give us the link between classical support vector machines and quantum support vector machines. I mean, the simplest possible link which we can have. Now, if we look at the standard quantum mechanical superposition of eigenstates of a given problem, so this phi of n, then we know that these coefficients c of n, they are simply given by the overlap. So these are normally called the overlap coefficients. So these are just the overlaps between these functions phi of n and this specific function phi of x, which may not be an eigenfunction of the operator itself, but is now actually a linear superposition of all the eigenfunctions. So the functions which we get, these overlaps, we know very well that the overlap squared plays the same role as a probability. So this is now going to be the same as this phi of n of x, and then it's squared. And later we are going actually to recognize this one as the kernel itself. Now, the other thing which we know very well is that if we calculate the expectation value of the Hamiltonian at hand of this specific h here, this is nothing but the sum over n of m, and then we have a phi of m, phi of n, and then this is multiplied with the coefficient Cn, and then we have h, and multiplied with phi of m of x, and then we have the coefficient C of m. And since these are eigenfunctions, we know that h acting on phi of m gives us the eigenvalue. So this is nothing but the sum over n of all the possible states, and then the probability of being in that specific state, which is this overlap coefficient squared. So if we then give a labeling to this state as well, and we compare this equation with the one which we had here, this one. So let's just write it down now. So comparing, and if we then compare equation x and double x, what we could do then, so we could think of using the quantum system which we have here. system as a kernel machine, as a kernel and in that specific case, what we would do then is that we would take the energy levels. So that means as a kernel machine by tailoring the energy levels, which we have labeled as an E of n here, as the labels, let me just correct that one. And these are the labels y of I, which we had previously in the definition of the Lagrangian, and exploit this quantity here, the overlaps, phi squared, as the same as some kind of kernel function, as some type of kernel function. So we are missing these parameters lambda. What we could do now is to introduce the parameters lambdas as well. And we could now think of looking at another type of observables, another operator. We're also going to use a simpler notation here. So these states, we are just going to replace them by the symbol n. And we could now think of an operator which is now expanded in this spaces. So we are just using a spectral representation. And we could think of this being given by this new parameter, lambda of n, where we introduce the Lagrangian multiplier. And then we have the spectral expansion of an operator. And we have assumed, obviously, that this operator H and O, that these operators, they actually commute. So that means that they have the same eigenstates. But the quantity lambda n is unknown. So what we use now is simply the spectral representation of an operator. That means that if I now calculate the expectation value of a given operator for this state phi, this is now the same as this sum of n's, which in principle is infinite. And we could call this an O of n, which is the observable of that specific operator, and multiplied with these overlaps squared. So this mimics, if we now think back to that equation which we had previously. So let's now look at this equation here. You see now that this mimics to a certain extent, if we go back a little bit, it now mimics this expression which we had here, where we now have this O of n, and then we had this function here, which is a kernel, and then you can think of this f here as the expectation value. So this equation here mimics f of x in this expression which we set up earlier. If we identify this kernel kn of x, this is now our kernel here, with this function n, or these overlaps. So to fix a formal identity, we have to set a correspondence between each data set, xn, and then each energy level, E of n, and we need a state phi, which then depends on this input x. So in order to really set up this correspondence between the classical kernel and what is going to become our quantum mechanical kernel, we need to find a formal identity which maps or correspondence, which links the data set Xn, which will be a classical data set. This is the typical situation. The data set which we're looking at will be a classical data set, and each energy level of a specific quantum mechanical system. And we need a state phi, which then depends on this input X. So fitting the data set then fixes this parameter lambda n, which we have here, this one. And because the energies are quantities which we know, so it fixes the data set, and also that corresponds to finding the operator O, which we have here, such that its mean value gives this target function. So if I now set up this quantity phi of x, and I bring back the x dependence and this operator phi of x, this is going to be equal to this function f of x, which we defined in the classical support vector machine. And then we can say that a quantum mechanical system is equivalent to a kernel method, and the coefficients lambda n fix the operator O. Now, the problem which we have to face is that it is not straightforward to realize a quantum mechanical system with energy levels E of n equal to this Y of n, so they should correspond to that, or to measure this operator O. So we need also a number of energy levels which equal the elements in the data set. This is again also not trivial. And when we use the spectral decomposition of the operator, we also have to make a mapping. So what we would need then is a mapping from the data set X of I over to this new function phi of X of I. So this is now a state, a quantum mechanical state, and we would assign the labels Y of I when we observe such a state. So we would also set up a mapping. We have to make a mapping from X of I to a quantum mechanical state and we need to assign the label Y of I when we observe such a state. And assign this specific label Y of I when we observe such a state. So in our case, what we have in general, when we look at a quantum mechanical operator, O here, and we use the spectral decomposition and add this Lagrange parameter, we would then have a sum from 1 up to n, and then we would have a lambda of I, which becomes the parameter we are going to have to find. Y of I is now given by the output from the data, and then we have the X of I multiplied by this phi of X of I. So this is a quantity which then would be given by the standard spectral decomposition of an operator. So in general, these states do not need to be orthogonal, but we could actually construct them to be orthogonal. And this means that the function, what we are going to find now, this function f of x, is a function which will be linked with the kernel function, but we need to make a link now. So we are going to find this f of x is going to be defined by this phi of x of a given operator of phi of x, and the quantities which we are going to look at this quantity here. So we're going to have a lambda y of I, and then we have the kernel, which is going to be given by this specific basis, which we have, this phi of x of I, and this is then multiplied by this phi of x and squared. So our kernel now is going to be given by this function which you see here. So this is the k of x of I, of x as we defined it before. And if we now put a label on it, if we now look at a specific function which has a variable xj here instead of x, so that means that we can rewrite this in terms of I equal 1 of n of lambda y of y of I. And then we are going to have a k of x of I of x of j, where now x here is simply just replaced by x of j. And this quantity here would then be labeled as a kij. It's going to be a matrix. Within this is I and j. And you see now that what we can do is actually to rewrite this quantity as follows. So that means that this f of a given x of j is now given by I equal 1 up to n. And then I'm going to replace my lambda y times y of I with this quantity. And then I have a kij, where this kij is simply now given by this overlap of x of I or phi of x of j squared. So this equation, which you see here, this is an equation which can be solved by standard linear algebra methods on a classical computer, or you could implement a linear algebra algorithm on a quantum computer. So we have now a mapping which then is going to link the classical support vector machine with a quantum support vector machine, but where we now have to make a mapping where we take x goes over to this function phi of x. Now, another thing which we are going to discuss now is actually a small digression, and then this small digression is going to bring us back to a quantity which we discussed a little bit earlier in the semester, and this is called the density matrix. So let us have that as a quick reminder here before we move on a little bit. So the density matrix is something which we defined in the very beginning of the semester, and it plays a very important role in quantum computing and also in quantum mechanics, obviously. And what we are going to look at now is a compact way of writing this kernel matrix in terms of the density matrix. So if we think of the density matrix of a given state, we know that the density matrix, this rho of x here, is given by the outer product of the states. So this phi of x could be any state, and that means that we are going now to link the density matrix with the kernel, and we can actually show explicitly that this kernel which we defined, so we can show, and I will go through some simple examples first. So we can show that the kernel k of xi, xj, that can actually be written out as a trace of the product of the density matrix for xi multiplied with the density matrix for xj. And this is going to be the same as phi of x of I times phi of x of j squared. So let's look at the type of transformation which we are going to make now. So if you go back to the slides which we had earlier in or the Jupyter notebook. So let's just bring back the Jupyter notebook here. So one of the things which we need to do now is to encode the data, and then there's going to be some kind of processing. Now, the first part is normally called this quantum feature mapping. So we're going to map to a quantum state. So input data is first encoded into quantum state. And this process is actually akin to a quantum feature map. Then we are going to set up the quantum kernel, which we define now as the trace of the product of, this is actually the product of the two density matrices. And after we've done that, we can do the quantum circuit processing and finally the measurement. So in principle, what we are going to do then, when we are setting up a given state, we may actually have a given number of qubits, which could be the tensor product of, let's say, the different states prepared in state 0. And then after that, we are going to act on these states with a quantum feature map, which is normally a unitary circuit. And one of the typical uh, ways of doing that, which you will encounter below in the code examples, is to take one of the rotation matrices. So this state then depends on the input x, and the choice of u of x is analogous to choosing a classical feature map phi of x in the kernel methods. And common quantum features maps include amplitude encoding, embedding data amplitudes in the state vector, and angle encoding. That means rotations whose angles are functions of x. So let's look at an example here. Let's go back to the whiteboard and take a closer look at what this can mean. So if we just bring back to life the rotation matrices, which we met in the beginning of the semester, so we could now set up one of the classical ones. So this is a rotation matrix along the x-axis. And this is something which we now could define as E, and it's going to have x as an argument. And we could define it as -1. So this is an angle x half multiplied with sigma x. And one of the expressions which we put up in the beginning of the semester was simply that this is something which we can rewrite as cosine x half multiplied with the identity matrix, which is a 2 by 2 matrix, minus I times sine of x half multiplied with the sigma x matrix. And just to quickly remind you, the sigma x matrix is simply given by 0, 1, 1, 0. Now, this means that if we now look at the action of this one on a specific state, so we could now perform this type of rotations on a tensor product of qubits. If we just have one qubit, you could now think of this one acting on qubit 0. And we know that if we act on qubit 0, the first one is just going to give us cosine of x half. And the identity matrix acting on qubit 0 gives us just qubit 0. And so let me quickly remind you, this is the same as 1, 0. And then 1 is simply 0, 1. And we know that when sigma x acts on that state, we get minus I sine of x half and multiplied with qubit 1. So I can now set up the density matrix for this specific new state here. So that would be the same as that operation which we put up in the Jupyter notebook, where we have some u which depends on x and which acts on an initial state. And this is something which we now could define as our phi of x here. So let's just use this notation here. So we have now performed a so-called encoding part, but we haven't said anything about the processing part. If you go back to the slides, this is the kind of first operation which we would do. And what we have now is a linear superposition of two states. The thing which we can construct then is obviously we can set up the density matrix for this quantity. So we can define rho of x, obviously. And rho of x is nothing but this state, phi of x, and the outer product with the same state, phi of x. So if I do that, then what I will get is the following. So this is obviously a matrix. So I would get a matrix now which looks like follows. So I have cosine squared of x half, and I get this matrix 0, 0. So just to remind you quickly of that one, this is just a matrix 1, 0, 0, 0. Then I get a new term because I'm taking obviously I have to complex conjugate I of sine, so that gives me a plus, and then I times I is -1, and then I have a minus, so that gives me a plus. So I get a new term which runs like plus, and then I have a cosine of x half of sine of x half multiplied with 0, and then the tensor product with 1 here. So this is obviously a new matrix, which is simply 0, 1, 0, 0. And then it continues with a plus, a cosine of x half times a sine of x half multiplied with 1 and 0. So that's a new matrix, which just fills in a 1 here and then 0 for the rest. And then I have the final piece, which is now plus a sine squared of an x half of 1 and 1. So this will be the density matrix for that specific quantity. Now, if I now take the product of a density matrix for a state phi of x and a state phi of x prime, so then I can now look at the density matrix, which I'm going to label as the product. This is the scalar product of x and x prime. If I do that, this is the same as taking the trace of the product of these two matrices. So I have a row of x and a row of x prime. So if I do that, what I'm going to get is the following. So this gives me a k, the kernel of x and x prime. I'm suppressing vector indices and so on. And it's pretty straightforward to see that this is given by this squared product of cosine of x half times cosine of x prime half plus sine of x half multiplied with sine of x half prime, and this is squared. And this is going just, if we now use the cosine and sine relations, this is nothing but a translational invariant cosine kernel. And you will see that this one just translates into cosine of x minus x prime divided by 2. So this is a very, how to say, a very easy way of setting up the kernel with that specific density matrix, where we now did an encoding in terms of cosines and sines here. Okay, so what we are going to get then is a state which, oh, wait a moment. No, I made a small error here because I had a minus. There should be, there should be an I here. Let me just, yeah, that's correct. I made a small error here. There should actually be plus an I here. I actually wrote wrongly from my notes here, and that should be a minus I here. Sorry for that. Okay. So then when we square it, this is the result we get. We take the two matrices. So this gives us a cosine of x minus x prime squared of 2 here. So if we look at the kernel, this is nothing but a scalar product defined in the density matrix feature space, which then can be rewritten as the trace of the product of the two density matrices. So that means that if I go back to this specific function, which I defined, this function x of j, this is something which I can then rewrite in terms of I equal 1 up to all the data points which we have. We have this parameter theta of I, and this is given by the trace of the density matrices, 1 for x of I, and then rho for x of j. It's actually not so difficult to see that this is the case. So what we see now is the following computational model which we need to consider. So we have to map. So this is the encoding part, map all the points. All the points in the data set which we have in the data set. Into quantum states. Then we have to compute the scalar products. Using, so that's the scalar product of the defined in the density matrix feature space. And this would typically be done by using the quantum device which we have access to. Compute the scalar products by using a given quantum device, if you have access to that. And then when we now look at this mathematically, if you go back to the equation which we wrote here and look at this in a more simplified way, which we had in the beginning here, this is nothing but a linear algebra problem which we can obtain by inverting this matrix, which we call for the Gram matrix, in order to determine the weights. So the Gram matrix contained this factor here, or the kernels, and also these quantities here. So we can then, by inverting that matrix, we can then find the solution to the problem. So that means that we would invert this so-called Gram matrix. Gram matrix to determine the weights. And then we are basically done. And this model is pretty advantageous if the computation of the scalar products is fast on a quantum device. And also the inversion of the Gram matrix can be either done classically or using a quantum computer. And in the latter case, there is often not overhead in mapping the Gram matrix to a quantum state. If there is no such overhead, then you gain a further advantage. So what I wanted to do now is to switch back to the Jupyter Notebook and look at how we can implement this using software like PennyLane or Qiskit alternatively, if you prefer to use Qiskit. So the textbook by Conte has also a lot of these kind of type of applications here. Let me just do one small thing before we change gear a little bit. my laptop, so it was almost close to empty battery here. So let me do that. Okay. So let me switch from the whiteboard to back to the uh, Jupyter Notebook. So when we are now setting up this quantum kernels, this is basically the quantity which we are going to set up. And so the kernel here is actually the square magnitude of the inner product of the two quantum states. And another version which you will often see is actually the one which you see here. So the quantum kernel, which we now have discussed, is something we would set up by having to translate the classical data point x into a quantum data point. And this is normally achieved by some kind of circuit where we have either a rotation matrix, as we discussed earlier, acting on an initial state. So in this specific case, we would have just one qubit. And then we need a parameterized quantum circuit that processes the data in a way that in the end, we can apply a measurement, which then returns a classical value -1 or +1 for each classical input x. So that means that the most general ansatz has then a quantum circuit here. There is an encoding part here acting on a set of initial states. So if you go back to the image here, which we had, so there is an encoding part, which is represented by some rotation matrix, to give you an example. And this is what we discussed earlier. And then we would have a processing part, and at the end, we would have a measurement part. So many of these things are actually hidden for us when we now look at the software like Qiskit and so on. But the general procedure now is to start with some basis, which is our computational basis in terms of the different bits. So for this one qubit case, it's bit 0 and bit 1. If we have two qubits, we could then have four states, which would be states 0, 0, 0, 1, 1, 0, and 1, 1. And then we could continue along these lines and set up rotations on the different qubits. So we get the superpositions of state 0 and 1. And then the next step would be the one where we do the processing. So in the case of a quantum support vector machines, we are just going to use the kind of basic feature map to translate the classical data into quantum states and build the kernel of the support vector machine out of these quantum states. And then after calculating the kernel matrix on the quantum computer, then we can train the quantum support vector machine in the same way as we do in a classical machine. So the kernel then would typically be given by this rotation, which we discussed on the whiteboard. And we looked at this simple example of a rotation acting on a qubit 0 along the x-axis. But we can set up rotations along the z-axis, along the y-axis, and so on. So in principle, if you go into this article here, there's also no proof that the quantum support vector machine brings a quantum advantage. But I will give you some arguments below here for why there could be advantages. So what we would have then, if we have more than just one set of qubits, is actually to have now a set of such rotations acting on a Hilbert space of a given number of qubits. And typically now, what we often do, which also simplifies things, is that we look at interactions with only 1 to 2, or actually less or equal to 2 qubits. That means that we only let 2 qubits interact at a time. And for s less than 2 here, equal to 2, the product only leads to interactions of the type Ci, Cj, or Xi, Xj, and non-interacting term C of I. And then the sum of all these terms, that this sum and the sums of all these terms that are possible with n qubits. So the power of these quantum kernels, so there's a lot of blah blah here, which I just wanted to go through so that you have a little bit more the background, is actually the power of the kernels comes from the exponentially large feature space. So when you have an n-qubit state, that has dimensionality 2 to the power of n. So even a simple feature map using n qubits corresponds to embedding of a state x, which are classical data, into 2 to the n possibilities. So entangling gates in U of X allows for highly nonlinear features. And in principle, when you have a carefully chosen quantum feature map, that can actually capture complex structures in data that are hard to model classically. So you see now that with a given number of qubits, you're actually able to, and with entanglement, you can actually include highly nonlinear features which would not have been possible in a classical support vector machine. So when you estimate these kernels, you would typically have two data vectors, x and x prime, and you need to compute this quantity here to find the kernel. And in PennyLane, if you use that as a software, and the example which follows here is a typical PennyLane example. So you could prepare this phi of x by setting up the transformation like we did here. And then you would apply the Hermitian conjugate and measure the probability of returning to the state here, which is now a tensor product of states in qubit 0. And that probability is actually given by this quantity which you see here, which is our kernel. So if you use PennyLane, there is a feature which is called angle embedding. And I provide a small template here for how you can do that. So that would be the first part. And in this specific case, we would import PennyLane as a library. And a typical import is a QML. There is a quantity which is called a device. So there's a default qubit, and I'm having two qubits here. I define a function which I call QNode. So this is defining my circuit that takes as input x1 and x2. It has the angle embedding, and then it takes the adjoint, and then it returns the overlaps. So it means when you set up this angle embedding and then the adjoint here, we're actually setting up this operation which you see here. And that returns the kernel. So this is what it returns. In this specific case, I just define the kernel in terms of these variables lambda, x1, x2, and this circuit which I have defined here. And then here I just have some simple data which I put in, x train and x test, and this sets up now the kernel matrix in terms of these two vectors, x1 and x2. And you just have to make sure that it has the right dimensionality. This, what you see here is just a plain test case here. So the angle embedding x1 encodes the vector x1 into two qubits via rotations, and the QML adjoint applies inverse embedding. And the output probability of measuring the 0, 0 state, so we have two qubits, is exactly the squared overlap of the two embedded states. When you use this kernel function, PennyLane computes then the kernel matrix, Kij, efficiently for training. So it actually has this utility which we used here, which is called the kernel matrix. So this is extremely useful for the first stage of our quantum support vector machine, which is this part which we see here, the encoding part. So if we scroll down then, after we've done that, so now we have a quantum feature map combined with a kernel. So this is the transformation we did. This is a quantum feature where we had the rotation, and that's combined with a kernel, and that defines a quantum support vector machine kernel. And the intuition now is that the quantum device is implicitly computing a rich similarity measure via its high dimensional state space. That is what we hope for. And this is analogous to the classical kernel trick, but potentially more powerful. So quantum kernels can potentially offer advantages over classical kernels, such as speed up, accuracy, flexibility, and robustness. So I see we are getting close to the end. So next week, we are going to wrap up the discussions on quantum support vector machines, and we are going to look at some examples on feature maps. And one example which we had on the whiteboard was an example of the 1 qubit and acting on that one with a rotation. We are going to look more at the amplitude encoding and also entangling feature maps. And then at the end, we are going to look at the different kernel estimations on quantum devices and how we can set up a simple example where we now include some classical data. So remember now that what we are doing is supervised learning on classical data. This is the kind of limitation which we are going to stay with. So I'm going to stop here